For lesson 9.6, we are looking at the binomial theorem, otherwise known as binomial expansion. You would have seen this back in Algebra 2. This is Pascal's triangle that we'll be using here in just a minute. I'm going to come back to that. So let me kind of show you where this begins, and I'm going to come back to that triangle in just a minute. If you were to get a problem like this, if you were asked to expand x plus y to the fifth power, one way of doing that would be to multiply x plus y times itself 5 times. But that would take a really lengthy process of distribution in order to come out with the result that you see here. That would take a long time. So same thing even with something like this. You know, with something smaller, if it was like x plus y squared, well, you know, we typically use what we call FOIL to do something like that because that doesn't take that long. But when you get into some of the higher powers, there's got to be a quicker method to do this rather than just multiplying something by itself that many times. So here's where all this begins. Anytime you're asked to do an expansion like this, it begins with Pascal's triangle. So as we come back up to the beginning right here, this is the first step in your process. The numbers that you see in this triangle, I'm not going to go into too much depth on this, but they do come from combinations. You've seen these in the past when you do probability. We do NCR for combinations. And so that's where those numbers come from. What you need to know how to do is how to build the triangle. So the easiest place to start is with the 1, 1, 1 setup that you see here. So think of this as row 0, simply because anything to the 0 power is 1. And so that's where that comes from. But that's row 0. So in the first row, you got the 1 and the 1. Each successive row, all you have to do is you always put 1s on the outside, and you fill in the gaps by adding. So if I have a gap right here, then I'm going to do 1 plus 1 to get 2. And so that number would fill in that gap. So as I move down, again, I always put the 1s on the outside. And then if I have a gap right here, I'm going to add 1 plus 2 to get 3. Got another gap right here, so I'm going to add 2 plus 1 to get 3. And you would just keep doing that as far as you need to get the numbers that you would need. So for any row, these rows represents the power of the problem that you are expanding. So if I have something to the third power, then I'm going to use the row 3 numbers for that problem. So this would be something to a fourth power, this would be something to a fifth power, and I could go as deep as I needed to depending on the exponent that I'm working with. So for the problem that we're beginning with on this, which is the x plus y to the fifth, that's how this one would start. So I would start by laying out the coefficients for row 5, which if you can see these, I would have a 1 right here, then a 5, then a 10, then a 10, then a 5, and then a 1. And so those are the numbers that we're getting right off of Pascal's triangle. And so that's how all of these would begin. So again, if you look at example B, it would be the same idea. I would look at the row 4 numbers, which are 1, 4, 6, 4, 1. And so that's how I would lay those out first to begin any of these problems. So it starts with Pascal's triangle. Then from there, you are putting in place what we call the A term and the B term. So 2x would be the A term, and 3y would be the B term. And so for each term, I'm going to place, so behind the 1, the 4, the 6, so behind all those coefficients that we laid down, I'm going to put the A term and the B term. So I would put a 2x and a 3y behind every term. So that would be the next step in the problem. And then for your third step, and this would be the last step of your setup, is you got to fill in the exponents. And as far as the exponents are concerned, we tend to just start with the highest power and work our way down. So over each A term, so remember your A terms are the 2x's, you start with a 4 and you work your way down. So I got A to the 4th, A to the 3rd, A to the 2nd, A to the 1st, and then A to the 0, you'll notice there's no A term on this because anything to the 0 power is 1. And so you don't need to show the A term on this one. Over the B terms, you go the opposite direction. You start with 0 and you work your way up. And so if I had a B term here, it would be to the 0 power, which is why you're not seeing it. Then I would have B to the 1st, B to the 2nd, B to the 3rd, and B to the 4th. And so after you lay out all the exponents, now your problem is set up, and all you would have to do is simplify each term. So notice each term is separated by a plus sign, and so I just go after each term individually and simplify whatever I can. And so you'll notice on the first one I have 2 to the 4th, which gave me 16, and x to the fourth. And so that is the first term of this problem. So moving down from there, again, you just clean up. This is your second term right here. So I'm looking at 4 times 2 to the third. So 4 times 8 times 3 gives me that 96. And then I throw in the variables. So I had an x to the third and a y to the first. They get attached to that as well. And so those are the variables, and you just go on down the line and you do that for each term, for that, and that, and then you get this ending look here that you see here. And so it's that same process every time that starts with Pascal's triangle. You then place your a term and your b term behind each one of those numbers. You then throw in the exponents, and then you simplify as much as possible to get this type of a look. So these are just some more examples of the same thing. So you can give these a try on your own. I'm not going to go in too much depth on this because they're all the same idea. So even for something like this, you would go up top and you would find your row 6 values. You would lay those out first. So these are what the row 6 values would look like, is the 1, 6, so on and so on. Behind each one of these numbers, you would place your a term, which is negative x, and your b term, which is 3. If you did it from here and called 3 your a term and b negative x, you would still get the same answer that I'm going to get. So it doesn't matter. It would be in a different order, but order doesn't matter when you're dealing with addition, and so that would be okay. This would just become your first term, your second term, your third term, and so you would have all the same terms. They would just be in reverse order, but that's not wrong. It's just a different format of your answer, and so that would be okay. But do consider this, because as we move forward to the last part of this, because order doesn't matter, as this might be somebody's first term, this might be another person's 7th term had they started with this as their first term. And so we usually don't identify these as a first term, second term, and third term. We usually identify them as, this would be identified as the x to the third term, or this would be identified as the x to the fourth term. We identify them that way because you can change the order, but this gives you a way. If I refer to this as the x to the fourth term, then it doesn't matter which order it's in. I'm still talking about the same term. Do notice one last hint on these. If you have a minus instead of a plus, your answers will always alternate signs. And so you would have kind of a plus, minus, plus, minus. You'll always have that pattern if you have a minus sign instead of a plus sign on these. So moving on down here to the last part, there is a formula that was up above in the notes, but I'm going to show it to you right here. It is in your formula packet. So here's where we've been this whole chapter, is with those guys right there. If you go to the bottom of that page, if you go to the bottom of that page, you get this formula that you see right here. And so this deals with the binomial expansion, and this is what we were just talking about. No one ever really uses this formula. We use the whole idea with Pascal's triangle instead. But there's one thing out of this formula that you really need to get, and that's this piece of it right here. So that, trying to highlight just what you need here. I don't think I'm going to get that. But anyway, if you just look from right here, this area, right, this formula identifies each term within your answer. So I could use this formula to get my first term. I could use this formula to get my second term, so on and so on. But this is a formula that you have in your formula packet that's going to help you with the next part of this process. When they write this as n over r, that's the same thing as writing NCR that we use for combinations. So do keep that in mind. In your calculator, you're not going to see it like this. You're going to see it as NCR. And so that's the combination part of this. A is your first term. B is your second term. N is the exponent that you would see. So if this was, x plus y to the 5th power, n would be 5. And then R is something that you have to come up with for each individual problem. So if you don't already have this down, identify this or write this down, and then let me show you how it's going to be used for our purposes. So here are 2 questions that formula would come in handy for. So when it says find the term containing x to the 8th, so again, that's, they don't identify this as the first term, second term, third term. Because the order can change, they would identify it as the x to the 8th term. So we are finding the term in the sequence that would have x to the 8th as its variable and exponent. So to do this, if I'm only looking for one term, I don't really want to do the entire expansion just to get one term. So instead, we use the formula that I was just showing you in order to find it. I'm going to show you a little different way than this shows you. This doesn't model the formula exactly, and even though it gets the right answer, if you're going to use the formula packet, I want to make sure you can use it properly. So if you're using the formula packet on a test, this is the formula that you would see, is this one right here. That was the one I just pointed out earlier on in the video. So if I sub in the information that they gave me, so 10 was the n value, that was the exponent, right? This is my a term, that's my b term. The one thing we don't know right off the bat is the r value. So remember, what we're trying to find here is the x to the 8th term. So we would look at this and say, okay, what does this need to be? What does r need to be in order for this to be the x to the 8th power? Well, that would make r equal 2. And so now I could fill in 2's from my r's, and that gives me this look that I see here. And the rest is just calculator and simplifying. So if I did this in my calculator, 2 to the 8th, x to the 8th, negative 4 squared, and I clean that up, I get to this answer. And if you model it after this way, instead of what you see on those note pages, this way you can take advantage of the formula that's in your formula packet in order to get this answer. I'm going to do the same thing for the second part of this one right here. So notice on this one is asking you for the term independent of x. This is a test question. I'm just going to tell you right now, so make sure you know how to do this. This will come up on a test for you. Independent of x simply means it's a constant. There is no x attached to it. If you look up at any of the examples that we had up here, right, this is the term that we would call independent of x because there's no x on it. Well, how do you get that? You have an x to the 0 power. So my goal is to figure out, using the formula that I have, I need to create an x to the 0 power in order to make this work. So that's the goal on this. So if you look at the example I'm going to show you, and again, I'm going to do it a little different like this one so that you can actually take advantage of the formula that's in your formula packet. So either write this one down or keep this in mind, but this is my a term, this is my b term, n is 9. And so if you look at this one here, and you can either pause it and go through it yourself, but here's the explanation. So that's the formula that we have. Again, if I plug in what I do know, right, a term, b term, this is all that stuff. And so remember, what we need on this is I need a 0 exponent. Anytime you are multiplying two terms together, we know that we add exponents together. So if I did 2 times 9 minus r plus negative 1 times r, that must equal 0 in order for me to have a term independent of x. I'm creating a 0 exponent. And so that's where this setup comes from. And if I go through and solve it, I get my r value of 6. And now based on this, now I can go back and fill in a 6 for my r's here, here, and here, and simplify. So I replaced my r's with 6's, and that gives me the look that you see here. And now I would just go through and clean that up. Notice I have a term that's independent of x. I have this came out to be x to the 0 power. If you see right here, this is 2 times 3, which is 6. Right here, this is a negative 1 power. So I have a negative 1 times 6, which is negative 6. When I go to add those together, I get 0. So that creates the term independent of x because it's x to the 0 power. So let me know, come in and see me if you have questions on that, but this is definitely one that you need to know.